Hello everyone, this is Professor Jeff Wilkerson at Luther College. This is an update just for the Physics 152 students, the General Physics 2 students here, sort of as we head into week 3 of our Index of Refraction Measuring Lab. I'm going to give you a little bit of feedback on what I saw. I've sent you stuff, responded to your intermediate lab reports. And so, but there are a few things I want to point out overall to make sure that everybody sees. And I thought that we'd go ahead and record this in video because I know that some people can't be in lab and have to do a makeup lab. And this way everybody hears the same thing in the afternoon lab and the morning lab. And it's here for posterity's sake. You can refer back to this as you want to refer back to this. So what we're going to do is you're going to pull all this together and you're going to write a final lab report. And I've got instructions out there for the final lab report, or we'll have them out there very soon, depending on when you watch this. And so, thinking about everything that we've learned so far, the intermediate reports that you've done each week have been guiding you in that direction. So you should lean on those heavily as you think about preparing a final report for us for next week. So what we're going to do here, what I want to talk about, so I asked you to report the mean and uncertainty, your best guess at what the index of refraction was for green light in the block and what it was for red light in the block. And so we did that pretty well. Our best guess at the index of refraction is going to be the mean, plus or minus the standard error, which is the standard deviation divided by the square root of the number of measurements that we made. And we made quite a few measurements, maybe not enough to be able to tell the difference between the index of refraction for green light and for red light, but we did a pretty good job here. And so this looked pretty good. One thing I would like for us to practice doing is to say, suppose that this number ended up being 0.003, which it was for a lot of people. That was a pretty typical number. Then what you want to do is you want to report your measured index of refraction, your mean, to that same number of decimal places, 1.456. For example, so that you match up in that last spot. Don't go reporting this out a whole bunch more than what you have right here. Now, what I might do, especially if I have a small number right here, there's different people will have different ideas about how to do this. But if I have a small number in this last digit, I'll often include the other digit. So especially if this is like 0.001, I'm going to include this next digit that's out here because there's a big difference between 0.0006 and 0.0014, which this could be any of those values, right? And that's more than a factor of 2 difference in your uncertainty. And so when we go doing z values and trying to find out probabilities that are 95% confidence intervals, or probabilities that are 2 values for green and red are different that we measured, it really makes a difference whether that extra digit is out there. So probably, a lot of times I just keep 2 no matter what. If this is a 9 or an 8, it doesn't add that much to you to keep 2, but it doesn't hurt that much either. Some people think it looks messy to keep that extra digit out here, but I'd be inclined at this point to say if that's a 2, go ahead and put that out here, and then whatever that next digit was out there. So anyway, that's what I would say, is just make sure the number of points after the decimal point matches that up here. And I'd probably keep 2 digits of precision out here most of the time. Keep 2 digits in your uncertainty, just because it gives us a little bit better, we avoid some rounding error issues when we go to calculate probabilities later on. So that's what we have there. So then when I asked you to find the 95% confidence interval for your index of refraction for each of these, once again, we want to remember there's nothing magical about 95%. People just use it a lot. We're not getting to this level where we're not going to say, hey, it's statistically significant magically. Somehow it's statistically significant if it crosses just barely over some arbitrary threshold. So we use 95 because that's what people use a lot. We may use a different value in the future. I may ask you for the 80% confidence interval sometime, just so we remind ourselves that there's nothing magical about this 95% level. And people did this the way we wanted to. We took 1.96 times that value. And what I would really like to see to report that confidence interval, though, is the interval. I want to see the mean minus that to the mean plus that. So I actually want to see a number that would look like 1.4283 to 1.4785. That's what I would think of as the 95% confidence interval there. So we can actually visually see what that range of index of refraction values was. Now, we did a pretty good job with the question about asking you whether you had measured, what was the likelihood you had measured a difference of index refraction between the green and the red light. And so for your block. And so that, and that work, what we do there, the way we were approaching this, there are different ways we could approach this, but the way we were approaching this was to take N of red minus N of green, for example, and or vice versa. N of green minus N of red is probably what we were doing. N of green minus N of red, and we get some number that's out there, and then we took that number and divided it by the uncertainty in these two values. So one of the things I wrote for people there is when you're giving me, you're showing me, telling me this result. Don't just tell me this result. You need to support that result a little bit. Argue your way through it just a little bit. Let me see, because I want to be able to provide you feedback directly. Let me see how you're doing this calculation. So we got some number out there that was, say, 0.021, let's say. And the uncertainty, we added the uncertainties in each of these in quadrature. Let's go back a little bit. There's an open question, and people addressed this pretty well in what they did, is to say, we calculated the mean and the standard deviation, the mean and the standard error, two different ways. One, we found the mean by just taking column statistics, just doing straight statistics of all of the values that we measured. We got the mean and the standard deviation that way. And then we made a histogram and we fit a Gaussian to it. And a lot of people wanted to know why that wasn't the same. Those two values weren't the same. And in part, it's because there's just different ways of approaching how we're analyzing this data. But the mean, when we did the Gaussian fit, it's the mean of the fit and the standard deviation of the fit, not of the data, but it's the best fit to the data where we've minimized the differences from that fit curve. And so we're using this as a proxy. We're using this as a fit as a fit for our data to say this is what we think our data looks like. Now there isn't one right way to do this or one wrong way. We've been trying to emphasize that you want to look at that and think about how this works. If you have a significant tail on this histogram, Gaussian fit's not going to be very good. If you don't have enough data in your bins, you got a lot of noise in your bins jumping up and down just because that's the way it is. And so the Gaussian fit is going to have quite a bit of uncertainty in it, and you may not be doing a good job with that Gaussian fit. On the other hand, if your data has a bunch of outliers in it, out in here, the Gaussian fit does a good job of saying, we're not going to weight those as much as we are the things that are in the center of this curve. And it does a pretty good job right there. What you found for most people, when I looked through the data for most groups, what we found was it didn't make that much difference. You actually got a pretty similar mean and a pretty similar uncertainty doing it either way. And you can just argue your way through. You can do it both. You write the paper, you can do it both ways and talk about the strengths and the weaknesses of doing it each way like this. And so you want to think about that kind of approach to that data analysis. But now, we take this uncertainty, we add the red one and the green one in quadrature, add the square of them, add them together, take the square root, and that's our uncertainty and the difference. And if that ended up being 0.004, let's say 0.004, see if I can do this right, 0.0042, then this ended up being a 5, we take this number divided by this number, 0.021, divided by 0.0042, okay? And to say, okay, this is 5 of these is basically what this is. And so we would say that's 5. And then we have our table, our Gaussian integral table, where we look that up. One thing to keep in mind, and I wrote this on papers when I saw it, one thing to keep in mind is that Gaussian integral table that I provided for you is a one-tailed test. It tells you that just given this uncertainty, just from the scatter in the data, just from our general going about our business and making measurements and getting this scatter in the data, how likely are you to find a difference that's this big or bigger given this? And in this case, not very likely. 5 standard deviation effect, a big effect. And so, but it's just measuring out here on one tail. And so you really need to multiply that by 2 because we could miss high or low, either one, right? We don't know. This could have been minus 0.021 just if it's noise, just as easily if it's uncertainty, I should say. Minus 0.021 just as easily as it was 0.021. So we could have missed on this tail or on this tail out in here. And so you need to multiply that result in that you get in the table that I provided for you by 2 to get your percent likelihood and your confidence intervals right there. So anyway, when you looked up the likelihood of, that's what that table's telling you. It's telling you how likely it is not to be, these are not to be the same. Most people did that, did a good job with that. I liked what I saw right there in what we did with that index of refraction. Now, most of the rest of the questions were about understanding that there are limits to what we're trying to do here. And we've talked about different ways that our work is limited in trying to measure this index of refraction. And really one way to think about that is this, is to say we could spend the rest of the semester going into lab every week and spending 2 hours measuring the index of refraction, just going bam, 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 so that this end gets huge. And the way we've been processing this data, that would imply that our uncertainty is getting arbitrarily small. We're getting almost no uncertainty. What we know, when we've had this accuracy versus precision discussion in the past, what we know is that there's a limit to what we can do there. To say that we know that there's going to be just anything there's a lot of things that could cause this mean to not really be the index of refraction, to be shifted off a little bit. Just straight up parallax in the way you're looking at the light as it comes through. If you're not looking perfectly square at it, or if the block is tilted just a tiny bit, or if the block isn't cut. We think our block has a flat face across there, but it might not, right? It's not perfect at all. There's all kinds of things that could lead this to be shifted one way or another. And at some point, we don't always know what that point is. It's our job to work to try to figure out what that point is, but it's hard work, and we'll practice it a little bit in this lab, but we may not practice it a lot. But we just need to be reminded that at some point, that inaccuracy, that bias, swallows up the uncertainty, the statistical uncertainty, this uncertainty that we have out here, this precision. And there's no need to keep taking data. You could keep taking data, and think you're doing good stuff, and think you're getting better and better results, and more, the index of refraction better and better and better, just more and more digits out through there, and you're not. Because this whole thing is shifted off, this sort of systematic uncertainty that we talk about here. It's shifted just a little bit. So that's what these questions were about. Specifically, this next to last question says, if you double the number of measurements for each you have for each color of laser, green and red, how would you expect that to change the estimate of the probability that the index of refraction between red and green light is different from 0? What doubling would do, neglecting what we just talked about, any concern about accuracy up here, about this thing being shifted off, what that would do is it would get your uncertainty down. And if you doubled, it's going to get your uncertainty down by approximately a factor of 1.4, the square root of 2. It's that square root of 2 that goes in right there. So if you double these measurements, you're going to get about a square root of 2 better, which is going to make this number smaller, which is going to make this number bigger. And so what it would allow you to do is it would allow you, in theory, to measure smaller differences between the green light and the red light, and it's a good thing to do that. And so you have to look at your data as you head into the last week. You look at your data and you say, is it worth the time to double my number of measurements to try to get that down by a factor of 2? And the answer is maybe. Looking at some of the data that I saw, you might be able to do a better job of this, keeping in mind we don't have a great handle on the inaccuracy, on the bias, on the shift here of where this standard deviation, mean might be relative to the actual index of refraction. So that's what most of that was about, is thinking about those limits. And that's what we're doing. So you head into the last week. We're going to use the blue light as for much of this last week. Take more red light data and take more green light data if you want to, and get as much out of it as you can. And that's what we got. And then next week, we're going to start a brand new experiment, and we'll talk about that just a little bit. And we'll probably shoot a video for you, an introduction to that. We'll have that some instructions for ways to think about that posted here shortly. So hope everybody's doing well, and we will see you in lab.